No, go somewhere else. Yeah. Okay, thank you. Sorry. ¿El escritorio? Ah, el escritorio. Que volver con... Ya, dale. Hey guys, let's get seated. So we had a bit of a delay with the coffee break, but now we're back for I guess the second session of the workshop. So it's kind of loosely based around energy. So our first speaker is Alessandro.
Yeah.
Why don't you take it away?
Thank you. So, hello everyone. At my presentation, I'll talk about a Julia-based integrated energy resource planning model, which is it's an expansion planning model built using Julia, using JuMP framework for building constraints for a model. We also use Amazon Workspace Computing Service in our cloud computing service developed at PSR. And to solve the models, we use the FICO Express solver. And this expansion planning model have been used in several countries across Latin America, in several studies at PSR, like in several countries like Colombia, Nicaragua, Chile, Brazil. Today, I'm going to show some results and some summary results of these two biggest important studies that I made using this model, that are the Chilean study, that was the first major study using this model, and a Brazilian study that was so important as the Chilean one, but a smaller study. And we also have some clients that run the model by themselves in Chile, Brazil, and New Zealand. And this is it. Just a quick introduction about myself. I'm graduated in electrical and control engineering at PUC-Rio. I'm currently doing master's degree in optimization at the same university. And I'm an optimization engineer and developer at PSR since 2017. So just talking about some features, some of the main features of the model. It's an expansion planning model, as I said, with hourly resolution, addressing unit commitment and wrapping constraints, and an exogenous calculation of the system requirement reserve, which is the way that the model, dual with the renewable source intermittency and predictability. So since this kind of technology has an intermittency and unpredictability, the total system requirement reserve must increase given an increase in the penetration of this kind of source. So I will propose, and I'll show you how to calculate an exogenous calculation. So the system requirement reserve depends on the planned investment decision of renewable source plants. So just a little bit of motivation. I mean, renewables are in fashion. I don't think you guys need any motivation at all. But what's happening is that investment cost of this technology has been decreasing across the years, as you can see in these graphs. And besides that, the capacity factor of this technology are increasing. So we are in a scenario where the costs are decreasing and they are getting more efficient. So why not invest on them? Why not look at them? So this is a graph from Bloomberg, which shows that after 2007, the investments in wind and solar plants have been increasing a lot across the years. So that's why all the countries and PSR have been doing lots of research and studies in how system will behave with this high amount of renewable penetration in the systems. So what are the challenges? The German system was one of the first systems to achieve a high level of renewable penetration, which shows the world, which spread the word to the news that this kind of technology has these problems. You have some challenge that you need to address. So what are those challenges? In the left-hand side here, I show a typically week in May 2012 of the German system, where we did have some renewable, some wind and solar plants, as you can see in yellow and blue. But the conventional source in gray and purple have a flat generation and do some ramping services during the sunrise and the sunset, as they should, because they are flexible. They are a technology that needs to give flexibility to the system. But then when looking at the right-hand side, the graph shows that a projection of a week in May 2020 in the German system, when now the thermal ramping had increased a lot. So the projections are that the conventional source that today have a flat generation, in the future, in the near future, we have to ramping a lot and to deliver more flexibility to the system. And you can see in this graph that another challenge is that if you look at Sunday, where the loads are lower, we have the load fully supplied by wind and solar plants. As you can see, there is no gray or there is no conventional generation. This leads to a zero marginal cost systems, which is it's a problem as well. I'm not talking about zero marginal cost systems, but this may be a problem. So what are the consequences? The consequences are a high variability and uncertainty in the offer. Now thermal plants need to make large generation ramps. We have some hours of excess and lack of generation because, I mean, the winds can stop. So even if you have 10 gigawatts of installed capacity renewable plants in the system, they may not they may generation nothing during some hours. So your system may have some hours of excess of generation and lack of generation as well. So this brings the necessity to the system increase its reserve capability. So we need to have some thermal plants present in the system only for these situations where you have lack of generation because of intermittency and unpredictability of this kind of source. So we need to address. So you need more system reserve, and you need more thermal flexibility to ramp and to turn on and turn off whenever it's necessary. And one of the important things for us, since we are working in an expansion planning model, now thermal unit commitment, that for those who doesn't know, unit commitments, it's a binary variable that that means that if it's equal 1, then the thermal plants are turned on, and if it's equal 0, then the thermal plants are turned off. So the unit commitments now have a great influence on expansion planning decision. So expansion planning models must take this into account. So what are the challenge for the model itself? So we need to build an expansion planning model with an hourly time steps to address renewable and wind and solar plants hourly generation. We have to consider unit commitments constraints. And as I said, we need to address the system reserve requirements. So I call here a co-optimization of the expansion planning. So I will co-optimize the wind plants decision along with the reserve they will bring to the system. So the model will know if he decided to invest in a high level amount of penetration to the system, he will also require a high level, a higher system requirement reserve, a higher reserve. Then he will need to build more thermal plants to provide reserve, and then it will increase costs. So the renewable plants brings an implicit cost to the models that must be taken into account. And besides all of that, we need to solve a MIP with all of that in a reasonable amount of time, which is quite a challenge, actually. So, as I said, the model, which is called we call at PSR as OptGen. It's a big MIP where we aim to minimize investment and operation costs, subject to lots of constraints. So we are subject to investment constraints and operation constraints that model everything I just said. So we have generation constraints, transmission constraints, load balance, reserve constraints, and unit commitment constraints. So I will show some of the main constraints of the model, not all of them. You may ask me later or talk to me later if you want any more details. So just to state, we minimize objective function as simple as the investment cost, where it states that by big I times X, where X is binary variables that modeling the decision variables for each thermal, wind, solar, and each project of this inside the system. So X is a binary variable, and that if it's equal 1, the project is inside the system, so the model built it, and if it's equal 0, the model decides not to build it. And the right-hand side, it's the operating cost of thermal, hydro, and whatever has operation cost. So talking about talking about some of the main constraints, we have some generation constraints, just like hydro maximum storage, hydro maximum turbining, water balance constraints, modeling the hydro plant generation. We also have thermal minimum and maximum generation, where I introduce here the unit commitment variable, that is the Y. It's Y. And the first equation is the first constraint is very important, because a conventional thermal plants, if it turns on, a thermal plant must generate at the minimum generation. So that's what the first constraint is saying. If Y is equal 1, then the thermal generation must be between the minimum and the maximum generation. And that's why the commitment is very important, because if we were not considering the commitments, a thermal plant could be turned on in the system without generating at its minimum capacity. Then we must constrain the commitment variable by the investment decision, because if the project is not inside the system, it must be turned off. So it's just a constraint to guarantee that nobody will be turned on if it's not inside the system. And we also have wind and solar maximum generation. It's bounded by the current wind and solar generation scenario, which is big JS out there. We also have some transmission constraints, of course, maximum capacity flow between buses, and second Kirchhoff law. We also have the first Kirchhoff law, but it will be present in the load balance constraint that we show next slide. And I have a load balance constraint that have everything I just said: thermal generation, hydro generation, renewable generation, battery net generation, because batteries can discharge, generating, increasing the total generation, and can charge, decreasing the generation, taking some generation from renewables, from hydros, or from thermal plants, And we also have the first Kirchhoff law. We also have here in the right-hand side the deficit and load variables that are cropped by the slide, but never mind. So we have some ramping constraints for thermal plants, ramping up constraints, and ramping down constraints. And we model startup variables in order to computate whenever that thermal plant needs to be turned on, the system must pay for it. And this may be important while taking expansion planning decisions. So it's important to model as well. These are some investment decision constraints, just to guarantee that the model does not invest in the same projects in 2 times periods. So if the model decides to build the project, a specific project at the first period, that this is what it is, and he will be present in the system for the whole period, just to guarantee that just to take care of any solver instability or this kind of things. And here are the reserve constraints that I just said, where you calculate the system requirement reserve as an exogenous variable. So the first constraint is the reserve balance, which is similar to the load balance constraint, but now it's a reserve balance constraint. So we send the available reserve allocated by each of thermal, hydro, and battery plants. And this total reserve must be higher than a system requirement reserve. which here is in the right-hand side, but it's actually a decision variable that I will show how we calculate. It's a decision variable because it depends on how much wind generation, how much solar generation you have in the system. So the reserve depends on how much the model decides to build of wind plants and solar plants. And the third and the other constraints are constraints modeling thermal, hydro, and battery reserve. The reserve must not exceed the total capacity subtract from the current generation, which is reasonable, right? So how do we calculate the system requirement reserve? That's the right-hand side of the reserve balance. We first calculate what I call a forecast generation, which may be as simple as the average of the generation, or maybe user input data. I mean, the user can input the data to model saying, my forecast generation for these wind plants are as follows, and could be a input data, or we can calculate it before the optimization as the average. And then we calculate for each wind plant the forecast error. So here we calculate the current generation subtracted from the forecast generation, and this is the forecast error. And then we take the forecast error and multiply by the investment variable decision. This is one of the most important constraints for the reserve balance, for our reserve balance, because it's coupled the the system requirement reserve with the investment in wind plants by multiplying by X. So it's one of the most important constraints. Then we calculate an hourly variation of this forecast error. At this point, the forecast error is already the sum of the forecast error of all the wind plants in the system. So it's already it's everything. It's the whole system there. And then I like to see this as a probability distribution, where I could take the average, I could take a CVAR, but we proposed a convex combination between the average and the CVAR, and the clients, the users can choose two parameters, and depends on the risk aversion level and some kind of criteria and so on. So since all of these constraints inside inside an expansion planning models must increase the problem size a lot, we need to make some assumptions and approximations, because all the constraints just said hourly constraints. So we are building here an investment model with with a co-optimization of the operation inside the same problem, with hourly constraints, so with hourly time steps. So what we need to do, we need to make some approximations in order to run, in order to execute it, in order to make it tractable. So the first approximation is a holy horizon. So with a window of an year. So I solved the expansion planning model for the first year, and then I take the decision, fix the decision, go to the second year, and do the same. So for the second year, get the decision of the first and the second years, and pass to the third year in a holy horizon scheme. And another approximation is the most important approximation. It's a daily aggregation. So we aggregate the months of the year into seasons. So for example, we could consider literally seasons like summer, winter, fall, and autumn. So we could have 4 seasons per year, or in a more we could consider without any aggregations, just considering 12 seasons, which each season would be a month. So the season 1 could be January, the season 2 February, and so on. So taking this, let's take this example, this example where the season is months. Each month can be aggregated into 2 typical days. So besides considering the whole 30 days, we can consider 2 typical days. For example, weekdays and weekend days. In order to, instead of considering 30 days per month, which would result in 8,700 hours constraints, we aggregate each month into 2 typical days of 24 hours, which are 24 hours times 2 typical days times 12 months, which it's more or less 300 hours to build constraints. And and this is a quite good approximation. So just talking about some basic structure of the model, the model is built, is fed by a PSR database structure, which can be filled using the interface of our models. So we have a lots of database structures there. So we have a lot of countries, just like Brazil, Chile, and then we build a database, which is basically text files, CSV files, and then this, and then the model, the OptGen model, read those files in order to build all the constraints I just said, and then with all this data, it builds the constraint using JuMP, and then use the express wrapper in order to pass the constraints for the solver, for the express solver, and then solve the model. And then the whole thing is going back in order to take express results, and then the solver results go back to OptGen, and it's process the results and generate reports for the users, and that's it. The gray box that I grade there, OptGen and express.jl, are under continuous development PSR. OptGen is something that I've been working for 2 years at PSR, and express.jl is a wrapper built at PSR by Joaquim, which permit us to use Express Solver with JuMP. And they are both under continuous development at PSR. So, as I said, we made 2 important studies with this model. The first one is an international study at Chile, here in Chile energy system. The study was paid by the Generators Association. They were worried about what would happen with the maintenance cost given a high amount of renewable penetration. So then they want to know new methodologies and what will happen with the operating points, with the flexibility, the efficiency, given a scenario where the renewable penetration will begin Chile. So here in the right-hand side, this is a study that has finished last year, and the right-hand side here is the final workshop where Mario. It's impossible to see that here, but it's Mario, the president, the founder of PSR, showing the final results and final considerations for the Chile Generators Association. The second study is a study in Brazil. It's quite the same idea. It was not founded by any generator association. It was founded by GIZ, which is a German company that sponsors some projects. And the idea of the project was to address new methodologies to deal with a high amount of generation, of renewable wind and solar plant generation. And the idea of the project was to focus on the methodologies, and they were not so much worried about results. So which was a quite good study for us to develop the model, and so on. So I'll just show some results of the Chilean study. So for example, we had a 13 years horizon of this study. We have 54 scenarios, lots of thermal plants, lots of wind and solar plants, lots of hydro plants, and a simplified network. When we are solving an expansion planning model, we usually simplify the network because first, it's a good practice to simplify the network in order to take expansion planning decisions, and it makes the problem more tractable, more efficient. And all of this together leads to about 6 million constraints per year, 8 million variables, which 3 million of them are integers. So it's a huge problem. And how to solve this? We use FICO Express Solver, and we use an Amazon Workspace instance, which C5.9 instance, which has 36 processors and 72 gigabytes RAM, and memory RAM. And Express support helped us a lot, tuning the Express control parameters in order to make the problem solve faster. And they helped us a lot. The lead developer helped us a lot, which is Michael Pirgard. And all of this together leads to a solve time of about 240 minutes per year, which is a lot actually, but we spent a whole day running the models and take the results the next day. That's how it does. I think I'm showing some results. This is the incremental expansion decision in Chile. So as you can see in yellow, it's solar plants decision. You can see that the solar plants are penetration a lot there, because mostly because of that. There it's here actually. So mostly because of the Atacama Desert. So solar plants are in fashion here, and after 2027, the wind plant begins to enter, to penetrate, and this is mainly because after a high amount of solar plants in the system, the model sees that there are lots of wind plants here that generate a lot during the night and not so much during the day. And this brings a lot more benefit to the system, since even if solar plants are cheaper, solar plants are generating a period where the marginal costs are near zero. So it does not bring so much benefit to the system. But a wind plants that generate during the night, even if it's a little bit more expensive, it brings more benefits to the system. So that's why the wind plants begin to penetrate after 2027 here in this study. This model here has binary variables that are investment decision variables and unit commitment binary variables. So it's not so straightforward to calculate dual variables. What we do is we solve the integer problem using Express, and then we fix all the integer variables and then solve the resulting IP to get dual variables. Standard way to calculate dual variables. So all the dual variables of this model came from the second run. And here, just to show some marginal cost results of the Chilean system. At PSR, we usually call this expansion marginal cost and not operating marginal cost, because it comes from an expansion planning model. So talking a little bit about the Brazilian studies example study. It's a near horizon, 10 scenarios, a lot of thermal plants, a lot of wind plants, a lot of hydro plants, some battery projects, and a simplified network as well. The wind and solar plants of this study was clustered. It was clustered. So we didn't model each individually wind and solar plants. That's why Brazilian system gets smaller than Chile one, even if Brazil is much higher, it's much bigger. So we have 5 million constraints per year and 4 million variables, which 1 million of them are integer. Solving the model, all the same stuff. Express support try to help us, but in this study we had a little bit more of experience. Then we could turn the parameters by ourselves. So some results. It's not a surprise. A lot of wind and solar plants, some thermal plants for flexibility, and some battery plants for reserve. And the last slide. The installed capacity in Brazil nowadays is in the left-hand side, with 70. We are nowadays a country with 70% installed capacity, a hydro 70%. We are 70% hydro country, and more or less 80% wind and solar plants. And about 2036, the projections are that we became a 40% hydro country, with 30% wind and solar plant share. And as you can see, the total amount of thermal plants increase as well. This comes from 8% to 11% in order to provide a reserve and flexibility to the system. This is it. Thank you.
So we have time for a question.
Tem que matar o
Yes.
Eu que tenho
Yes,
que
I'm
botar
going to show you
a
ability. I also
Aqui tem uma mexida.
started development, so that is considered efficiency